Welcome back. In this brief lecture, we will look at certain important metrics for capacitors. So the energy of a capacitor is given by this formula. As the capacitor is getting charged or discharged, the voltage changes. So to get the integral of energy stored in a capacitor, we integrate this expression with respect to voltage. So overall, the energy is specified by simple integration to obtain this formula. This formula is fairly intuitive when you look at it from basic electrostatics. So this is the change in energy, and energy changes when you move some charges across some potential. So to make sense of this more intuitively, you can try to think through how you think about change in energy under gravitational potential. Um, so these formulas are fairly similar. So to look at the power is obtained in the following manner. So this is the general expression for power, and it can be shown that the maximum power which you can obtain from a capacitor is via this formula. It involves certain manipulation, which is not too difficult, but we are not going to derive that here. But this is the expression for obtaining the maximum power of a capacitor. So in this expression, the equivalent series resistance of a capacitor contains few components. This is the resistance from one electrode, from the other electrode, and besides the electrode, there can be other resistances, especially resistance due to the separator. So this is where electrolyte is stored inside the separator. So this would also contribute to the series resistance. And maximum power is an important quantity when you specify the characteristic of a capacitor. Typically, battery is seen as an energy storage device. A fuel cell is an energy conversion device, whereas a capacitor is an electrochemical device that gives you power. It's a power device. So the expression for maximum power is an important quantity that you should know how to obtain. This is probably the most important slide in this presentation. Here we are plotting along the y-axis specific power, so which is specified by watt per unit mass in kg, and you are specifying that against specific energy plotted in the x-axis, which is given by watt hour per kg. Why is this not very obvious? Is because what contributes to the mass of the capacitor is not only the electrode. The electrode is where you are storing energy. That is what is contributing to your energy as well as power. But besides the electrode, there are other components. The components are the main component which adds to the weight of a capacitor is the separator. So let us understand how to interpret this curve. There are two parts towards interpreting this curve. So how do we get very high power? Very high power is obtained when you can discharge the capacitor very rapidly. That would happen when you have a very thin electrode. So if you want to have very thin electrode, then you can discharge the capacitor very rapidly. So you would have high specific power. However, what is the disadvantage in this case? In this case, the ratio of the weight of the separator to weight of the electrode is relatively high. Therefore, For a capacitor with a thin electrode having high specific power, you would have low specific energy, because the energy storage component, which is the electrode, is relatively, the ratio of the electrode mass to the separator mass is relatively low. Supposing you want to, the other limit is the following. Supposing you want to get high specific energy, that means you have a thick electrode. So the ratio of the mass of the electrode divided by the ratio divided by the mass of the separator is relatively large quantity. So every component that is there in the capacitor, or all the major components, or the components which contribute to the mass of a capacitor, is involved in energy storage. So if you have a thick electrode, you can get a lot of specific energy, but the thick electrode does not get discharged rapidly, because there's a potential variation inside the porous thick electrode. Therefore, it takes some time for the capacitor to get discharged. So that is the trade-off. So if you want to get high specific power, you cannot have high specific energy. If you obtain high specific energy, you will not have high specific power. So the important thing to realize here is, besides the energy storage component, that is the electrode, there are other components which add to the mass without contributing to power or energy. So there are other parts. So here, what do we see? Supposing we are to increase the power, you don't want to be in this range, because for increasing the power by a small amount, by this amount, you are losing a lot of specific energy. Supposing you go by this amount and increase the specific energy, but corresponding to specific power, but corresponding to that, you are losing a lot of specific energy. The same thing is seen here too. If you want to increase the specific energy, let's say by this amount, within this region, in this region especially, you are losing the specific power by a considerable amount. So let's say you move from this point to this point, there is some gain in specific energy, but corresponding to that gain in specific energy, the amount of specific power that is lost is fairly significant. So it is not advantageous to stay in this region or stay in this region. So you want to be somewhere in the middle. So this is a good trade-off, wherein you get reasonable specific power and reasonable specific energy. So this trade-off has to be understood. So the last issue we would like to address is power loss. This is given by a simple formula, which is, you must have seen this in your previous classes in high school, I squared R. Again, the series resistance contains two contributions from two electrode, as well as from other components, mainly the separator. So how do you define efficiency? This is the energy delivered when you discharge the capacitor, divided by the energy supplied when you charge the capacitor. So this is the way you try to define the energy of a capacitor. For a capacitor, this can be a reasonably high quantity compared to other devices, like, for example, battery or a fuel cell. Relatively, for simple electrochemical double layer capacitor, efficiency can be rather high. In the next lecture, we will look at certain practical aspects of electrochemical double layer cell design and other aspects of performance of EDLC. Thank you.